let me start by welcoming you all to this webinar, to this CMCC webinar, and let me briefly introduce myself. I'm Francesco Bosello. I'm professor of economics and environmental economics at the University Foscari of Venice, and I'm also principal investigator here at the Euro-Mediterranean Center on Climate Change. And incidentally, I'm also coordinating the ACCREU project, which is one of the projects that is being hosted by this webinar. And indeed, this webinar aims to present the preliminary results of 3 so-called sister projects. And these are sister projects because they have been all financed within the same Horizon Europe call. And the main topic of this call is to better understanding the dynamics that are behind climate change risk for the EU, but also more in a broader sense, more globally. And these 3 projects, which are ACCREU, CROSSEU, and SPARCCLE, are now in a phase where some preliminary results can be presented, and we're very happy to share with you these our preliminary findings. And this webinar is also part of this cross-fertilization activity that is highly encouraged by the European Commission within the Horizon program. So we hope that this is just the first of this webinar series, and we are planning to have at least another one more towards the end of the project to present the final results. So we have very nice, skilled speakers today, and from all the 3 projects. So we are going to start with a presentation by Paul Watkiss from Paul Watkiss Associate, and focusing on some reflection on the cost and effectiveness of adaptation, presenting some results from the ACCREU project. So then, going in alphabetical order, using the project names or acronym as reference, we shall have Nicholas Vasilakos from the Norwich Business School, presenting the work on part of the work done by the CROSSEU project on climate shocks and climate inequality. And last but not least, we shall have Rosanne, Martyr, and Ann-Kathrin Petersen from Climate Analytics present the work on SPARCCLE, which is a presentation investigates the connection between climate risk and the pathways to climate resilience. And as a host, I also have the duty to introduce briefly to you, audience, what the CMCC, the Euro-Mediterranean Center on Climate Change, is and does. So I'm going to very briefly share a presentation guiding you towards the activities that CMCC currently develops. Okay, so you should be able to see my screen now. Please, Silvia, confirm.
Yes.
Okay, perfect. So CMCC is a multidisciplinary and multi-division, multicentric research institute, Italian research institute, whose research is focused on the interaction between climate change and society. This is our, let's say, leadership staff with our president, Antonio Navarra, the scientific director, Giulio Boccaletti, and the operation and administration director, Laura Panzera. CMCC is a non-profit foundation and also can be labeled as a charitable organization under the section 501 of the US Internal Revenue Code. So this means that we can attract funds from the philanthropy, but we have a huge network of collaboration with many international initiatives. The mission of CMCC is this on the one hand, improving the research methodology on climate change and climate change impacts. So we improve the methodologies and the modeling, but all this is aimed to improve our ability to provide scientifically supported support to decision making. So we would like to provide solution to the major issues related to climate change. And to do this, we have this multidisciplinary organization and multidisciplinary research focus. Basically, we are organized in institutes. I'm going to say something about the institutes in a second, and 4 strategic programs that are cross-institute. And we are supported by a very powerful computing infrastructure. We have some supercomputer here and specialized centers that support our researchers with digital innovation, education, and training. The institutes are thematic institutes. One is more climate science-based, one is more focusing on resilience, climate resilience, and one is more focused on the social economic issues and problematics related to the relation between climate change and the society. These institutes are connected somehow by the strategic programs that are cross-institutes. One is related to the geochemical and industrial carbon cycle. One is on coasts and the dynamics that are happening there on the coastal areas. One program is focusing on the social economic outcomes and how they are triggered and driven by climate change dynamics. And then we have one other program developing AI and machine learning technologies. All this is supported by centers, and we have the one centers providing the high computing power that we need for all our research, both social economic and the climatic oriented ones. We have one advanced digital innovation center. And finally, we have one center dedicated to training and education, also to bring outside CMCC to non-expert all the knowledge that we are producing. Just to say that we have a very powerful supercomputing center, one of the most powerful in the EU. And that we are producing a lot of tools within our research activity, from numerical models for climate simulation to software application to decision support system for the social and economic investigation and analysis. With that said, we have a lot of, we are constantly engaged in many projects, and yearly we are mostly around the 200 projects that we are involved in and from different sources, and we are also publishing a lot. Let me say, to give an order of magnitude anyway, to contextualize, that CMCC has more or less 300 researchers under contracts. And with that said, I'm stopping here, and thank you for your patience, and I will immediately give the floor to our speakers. And in particular, I would like to start with Paul Watkiss from Paul Watkiss Associates. And again, let me recall the title of the presentation, which is a reflection on the cost and effectiveness of adaptation. So, Paul, the floor is yours. You have more or less 15 minutes to present. And important, if you have questions, please write them on the chat, and we shall try to convey them immediately after the presentation, if there is some time left, or anyway, they could be they will reach the presenter and you will be answered afterwards. Thank you.
Thank you, Francesco. Can I just check that you can see my screen?
Yes.
Full screen? Excellent.
Yes.
So yes, the ACCREU project, I'm going to talk a little bit about some of our emerging findings. ACCREU is a Horizon Europe project, of course. We've got 14 institutes. I'm not going to go through them, but this is very much a presentation on behalf of the consortium. And in the project, as Francesco has set out, we're looking at the economic costs of climate change, the costs of inaction in Europe and globally, but we're also looking at the costs and benefits of adaptation. And that sort of really is a sort of evolution from some of the previous projects we've all worked on before. We've got a very strong co-design process, so we try and provide results that are useful for policymakers, but also try and integrate policymakers within our research. And because of that, we have a large number of case studies that I'll talk about very quickly later on. Now, diving straight in, we run a very large modelling framework in the project. And this, at the bottom, starts with a large number of sector models. So, for example, of sea level rise or river floods or agriculture. And we run those both at Europe and globally. And they're shown in blue. And we feed those in turn into European macroeconomic computable general equilibrium models. You can see that in green. And the combination from the sector models and the CGEs, we are then feeding into global models, including a set of global integrated assessment models. And they're shown in orange. Where possible, we try and run multiple models because what we're finding is that there's differences between the models, which are quite important. But you can see how the flow of the project goes forward. Now, complementing that, we also have some more national to local case studies on adaptation. I'm not going to talk about those today, but I do want to highlight that they provide really critical examples of real-world adaptation economics, and we're strongly working with stakeholders on developing them and taking them forward. So I got to dive straight in. We've recently completed our European results. They're available on a policy brief that was published, I think, on Friday, and I'm going to talk about a few of the results today. Obviously, in the time, I won't go through everything. But what we have done in the project is run a large number of sector models for a number of RCPs. We have done this for consistent social economic scenarios just because of the number of runs that we're doing, because we've also extended to look at the costs and benefits of adaptation. So we have a large amount of information here, which really is starting to provide some very useful messages on effectiveness, as well as on the benefits and the costs of adaptation. So I'm going to give you a few results now and a few reflections, and then tell you what we're also doing later on. So before I do that, I just want to explain a little bit about framing. What we're doing here is in terms of my bottom left picture, we're looking at the economic costs of climate change in our models first, the cost of inaction, and you kind of get this stylized increase in economic costs over time with greater levels of climate change. And then adaptation has a benefit, an economic benefit, by reducing those. But one of the things is that adaptation isn't always perfectly effective. And so we have this additional issue, which you can see on the right-hand panel, where we have some residual damage after adaptation. And that's really important for us because it means in all our analysis, there's a trade-off. There's a trade-off between the benefits and the costs of adaptation and the residual impact after adaptation. And that's important because it introduces a new thing, which is around decision paradigms on adaptation objectives. So I might decide that I will go and implement adaptation from an economic optimal perspective, an economic efficiency perspective, but also quite often we might implement adaptation based on acceptable risk levels because of this trade-off between the different impacts and residual damages. So this is important in the real world because what we find is different sectors actually apply adaptation paradigms on decisions slightly differently. The way that we do things in health, for example, is different to floods. And even within countries across Europe, we get differences. So, for example, while the UK, for example, where I'm from, introduces flood risk management from an economic efficiency point of view, other countries use acceptable levels of risk and return periods for floods. Right, let me give you a few results. What I'm going to do is just give you 4 quick examples from the projects with a number of models and tell you what the emerging findings are. So I'm going to start with coastal and sea level rise. That's always the one that we have the most information on. What you can see if you look at the top right is you see a classic picture of rising economic costs of sea level rise in Europe over time, exceeding 100 billion euros a year by the time you get towards late century. And you also see this strong pattern that with higher levels of warming, higher RCPs, you get greater levels of damages. What we also do is we then rerun the models with adaptation. And what we find is that the models are extremely efficient and very cost effective in delivering adaptation and reducing those future impacts. So you can see with adaptation, you get this dramatic fall in the levels of risk, which is good. And you can see on the bottom right where I've taken a snapshot of the year 2050. I'm plotting my benefits against my costs. Benefits are at the top, costs are in orange at the bottom. You can see these high benefit to cost ratios in terms of annual investments versus annual benefits coming through, and demonstrating, as I think we all kind of would expect, high levels of benefits compared to costs, but slightly better ratios when we have our optimal scenario, just because of the nature of that decision paradigm. Now, I'm going to give you an example for river floods now, and I also want to highlight the differences, and this is where it starts to get really interesting. So we have a similar pattern, and this is some work done with the Glofris model and the team from the Netherlands. What we have is rising economic costs, again, shown in red at the top. But what we also find here is differences between the coastal example and the river flood example with respect to RCPs. And one of the complexities here is river floods are much more complex in their nature, and you get increases in some areas and decreases in others, which gives us a different sort of pattern with respect to different RCPs. And whilst not shown here, that also is reflected with different climate model outputs. So that's one major difference. We then put adaptation into the model. And again, you can see these dramatic falls in blue and green with different levels of adaptation, and also differences depending on the objectives that we set. But what we also find is that the reductions aren't quite as dramatic as they are for sea level rise. So what this is showing us is we're having higher levels of residual damage, even with adaptation in place. Now, again, bottom right, looking at a snapshot for 2050, very high benefits to costs. That's really important, but a slightly different pattern between the two adaptation scenarios. And also what we're starting to see now is actually quite significant costs in orange going forward, because we're having to spend quite a lot of money to get the benefits that we want to see. And whilst those benefits exceed the costs, we are starting to see the ratios being slightly smaller than they are for coastal. 2 quick examples just for agriculture and cooling. I'm going to go through these a little bit quicker just because of the time that I have. We started to look at the agriculture sector. I'm sure everyone knows the sort of classic picture that I have in the bottom left, which is rain-fed crops with climate change in Europe. And you can see the strong distributional patterns of greater impacts for a selection of crops here, maize and wheat as examples, particularly for Southern Europe and into Eastern Europe, whilst slight benefits projected in the crop models for Northern Europe. And what we're doing in this case is we're using the Globion model, which is a partial equilibrium economic land use model. And that includes several adaptation options, R&D and farm level, but we're focusing here on irrigation, because irrigation is going to be one of the more, we suspect, one of the options which gets taken up and does involve potentially quite high costs. And so what we're looking at the bottom right is what the potential costs might be of irrigation to address those rain-fed impacts on the left. What we see again is a similar message is coming through. Irrigation appears to be very cost effective. It also involves relatively low costs compared to the benefits that we get. And also we can see those over time, and not shown here, but we've looked of course for different RCPs, which are shown in the grey error bars up and down. One of the other things that we've done here, though, is we've done some differences with respect to constraining assumptions. So all of these assume and are based on an analysis which also includes a water model. So we're ensuring that sufficient water available. But one of the questions is whether or not in Europe we will allow irrigation to expand to its maximum potential, or whether we will limit it. And it does seem that some of the potential limits that we might see are likely to be more important than actual the adaptation optimization itself. So what I'm saying is, left to their own devices, we are likely to see high levels of irrigation, and whether policymakers want to constrain that or not is likely to be one of the influences on uptake. And then finally, looking at labour productivity. So this is the economic impact of climate change on labour productivity. This is starting to become one of the really big issues in the literature, generating very high economic costs from the lost work time, particularly through heat, both indoors and outdoors. And what we've done here is we've focused on that indoor labour productivity issue. What we've assessed is high economic costs from those impacts over time, and you see those follow a very traditional pattern of higher impacts with greater RCPs and greater levels of warming. And we've also looked to see, with air conditioning as an adaptation option, how that might reduce those impacts. And again, a very similar trend in terms of reductions and benefits to costs being very positive. But also in this particular case, and this is partly due to the modelling constraints as well as the sort of the levels that we're assuming, but still quite high levels of residual damage. And again, quite high aggregate costs starting to come through to realise these benefits. So where does that leave us? I'm going to talk about this, and I'm going to give you a couple of other slides just to kind of highlight a few other points. What our new numbers are showing is high costs of inaction in Europe from climate change. I don't think there's a great surprise there. Starting to look at costs now that are potentially several €100 billion a year by the mid-century. But also looking at the adaptation costs and benefits, what we're showing is that those can be significantly reduced with adaptation. So on the one hand, there's a really positive story that adaptation can support and reduce the economic costs of climate change in Europe. But we're also finding that those adaptation costs are starting to add up. So we've, for the first time, really started to aggregate up our models. And what these are sort of indicating, and these are very indicative numbers, but it quite easily adaptation costs of €40 billion a year in 2030, at least rising to 60 billion a year by 2050, and potentially higher than that under warmer scenarios, albeit with large ranges, but sort of showing that these costs are going to start to become significant. And there will also be some residual damages even with adaptation in place. And that actually involves some really important policy choices about what society is prepared to pay and what society is prepared to accept with respect to those. And what we're doing now is we're putting those numbers into some European macroeconomic models. That's just started, and that will allow us to really look at the cross-economy effects, both in terms of impacts and adaptation. And just a final little couple of slides just to say what we're doing going forwards. One of the things that we've been doing is complementing that modelling world with detailed literature review on the cost effectiveness and the benefit to cost ratios for adaptation. So as well as looking at individual studies, we've been looking at sort of umbrella reviews of existing reviews, if that makes sense. And this is really interesting because we did this 10 years ago in the EconAdapt project. And so this is almost looking 10 years later and saying, well, how has the evidence base improved? And the first thing that I would say is that there's a lot more evidence out there. So that's positive. What we're finding generally is that adaptation has high economic returns, mostly, but not always. And I do want to put this as a caveat. Adaptation per se doesn't always give you a benefit to cost ratio above 1, but we find lots of evidence that in many cases it does. But you can see just from a snapshot of some of our review data on the right-hand side, very large ranges. So the economic effectiveness of adaptation really does vary on a site and context specific basis, and it varies very strongly across individual actions and sectors. So we have to be a little bit careful in making generalizations. It's also worth highlighting, and this is a slightly complicated issue, but it's quite important. We're looking at the total economic benefits and comparing those to costs. It's also important to split out the avoided damage, the actual risk reduction, because some of these measures have high benefit to cost ratios because they're delivering co-benefits. And that's great in terms of they're beneficial, but it also means they achieve less reduction and therefore lead to higher residual damage. And there's some important issues here about that trade-off as well. And then the other thing that we're starting to find, which is really critical, is that the financial returns from adaptation are much lower than the economic returns. Now, what do I mean by this? The economic return is the societal benefit, so it includes both the market and non-market benefits. When I look at the financial returns, I'm only interested in the return from a financial private perspective. And what we find is that adaptation has a really strong public case, but when it comes to the financial returns, they're a lot lower. And that really explains why there's less investment in adaptation, but it also means going forward, there's a lot of challenges there. We've also started to look at the limits of adaptation. There's very little evidence on the economics of the limits of adaptation. There's a little bit emerging on the sort of physical and some of the other elements. It's very difficult to know exactly what this is going to mean, but we are looking now at sort of sensitivity testing to see what limits to adaptation might mean, and also what those might mean for our modelling studies, which our modelling studies tend to assume unlimited adaptation unless we constrain the model, as in that agriculture example. But I think in the real world, these are going to be much more important much earlier. And just to finalise, what we're doing now is we're taking
just 1 minute, Paul.
I'm only going to take 1 minute, Francesco, so that's perfect. We're taking that very rich information from different models and from the literature review, and we're trying to build that up into some highly stylized functions that allow us to look at the macroeconomic and the sort of global story on adaptation. So, for example, I've got an example in the top right where I've got my sea level model and I'm running it lots and lots of times. And that allows me to build up some relationships between damage and sea level rise, as well as adaptation costs and benefits with sea level rise. And then what I'm able to do, and what we've been doing recently, is using that information to generate potential curves that we can use, which allow us to look at the avoided damage, the benefits to costs, that will allow us to get some new functions for the integrated assessment models. And that's really useful because at the moment, adaptation is very stylized in those models. And what this new evidence will allow us to do is to start creating curves that are better representations of adaptation. And also allows us to look at sensitivity testing to see if we constrain the models with limits, how that might actually change that pattern and the global potential for adaptation. And on that, I'll finish. And I think I've just about hit to time, but sadly no time for questions, and pass back to Francesco. Thank you very much.
Thank you, Paul. We are receiving questions, but we shall address them if we have time at the end, or some of them. And you can also answer online the questions. So I will immediately give the floor to Nicholas. And I should say that I anticipate that Nicholas is sick, but he is anyway agreed to participate. So this shows the commitment of the research community in the EU in general, but he's not activating his screen. And then after presentation, he will leave. So unless he would like to stay, but Nicholas, so the floor is yours, and thank you for your double effort to be with us today.
Thank you very much, Francesco. Good morning, everyone. Once again, my apologies for the timing. There's never a good time to be ill, but I definitely didn't want to be ill today. Yeah. I apologize in advance if there is some coughing. I'm very well medicated for this session, so hopefully it will be fine. Thank you very much for inviting me to speak in this session. And Paul, very interesting presentation. In a way, it makes my job easier because I will be talking also about some aspects that relate to the effectiveness of adaptation policy. I will be presenting some early findings, UEA findings from CROSSEU on the relationship between extreme weather events and income inequality. I should say that the work I'll be presenting today is based on results that have been co-produced with my colleagues Shan-Fei Zhang from Norwich Business School, Katie Jenkins from Tyndall Center for Climate Change Research, and Nicole Forstenhauser also from the International Center for Climate Change Research, who are also my co-authors. Climate extremes are, as we all know, are not just meteorological anomalies, but also they are socioeconomic stress tests that reveal and often exacerbate underlying weaknesses in our societies and economies. And understanding, therefore, the distributional effects of extreme weather events is very important for designing effective and equitable adaptation policies. As we're going to see from the emerging evidence that we get from this work, not everyone is affected the same way. So I'd like to start. First of all, can I check that you can see my screen because I didn't ask?
Yes, the screen is okay.
Okay, so let me start with the first chart for today. I'll show two charts that highlight essentially the socioeconomic importance of climate change, starting with this one from the European Environment Agency. And it shows the economic losses from weather and climate-related extreme events across the EU over the last 40-something years, adjusted to today's prices. Three main points I'd like to emphasize on. First of all, you can see very clearly there is a lot of variation. Some years exceed 50 to 60 billion euros in losses. These are years when you had extreme weather events happening, hitting the continent, linked to floods, heat waves, or compound events. Also, you can see that the composition of the extreme weather events is changing over time. It used to be that storms were most important in terms of economic damage. In recent years, we see that floods and heat-related hazards have risen sharply in terms of significance. But also, if you do what I call inomics, if you just try to see how the change moves over time, you will see that the trend is pointing up. So average annual losses have doubled since the 1980s, and they continue to climb. So from a policy perspective, I think we will all agree that climate change, specifically extreme weather events, is not something that we can turn a blind eye on. It matters significantly, not only because people's livelihoods and lives are in stake, but also because precious resources have to be committed in a way that maximizes effectiveness. So let me move on also to a second chart that goes into a more finer detail, if you like, of how these impacts are distributed across society. And this chart is based on US data, but it really reflects patterns that we see globally. And it shows how, specifically this one, shows how heat exposure above 30 degrees affects mental health outcomes across income groups and genders. So the blue bars on the left show that the poorest report the most severe impacts, while higher income groups are less affected. And the red bars on the right highlight gender differences. Women consistently report greater mental health impacts than men, probably for many reasons, but probably also because of caregiving roles or employment patterns or access to support that they have. So we can easily see from the emerging data that we have from Europe, US, but also other parts of the world, that climate risks are not only physical, they are socially and economically patterned. Exposure may be similar, but consequences vary depending on who you are, where you live, and what resources you can draw upon. So the research I'm presenting today is about understanding better some of these effects, specifically the relationship between extreme weather events and income inequality. Lower income groups are more likely to work in climate-sensitive sectors, such as agriculture and construction. They're also more likely to have limited access to insurance or savings, and they tend to live in areas with higher physical exposure. This is all, if you like, facts that have been shown in previous studies. So they're therefore more vulnerable to some of the extreme weather events that I will be talking about today. And this results in a feedback loop. As inequality rises, adaptive capacity falls, further entrenching vulnerability. And over time, this can feed into social dissatisfaction, if you like, or even unrest, as we've seen in recent times. It can put migration pressures to countries, and it can also result in direct economic effects like long-term productivity losses of the sort that Paul was talking about earlier. This is why understanding the distributional impacts of extreme weather events is very important, especially for designing effective adaptation policies, but also climate policy in general and economic policy overall. In terms of methodology, what exactly do we do in terms of the econometric estimation of these effects? The core idea is that we look at income inequality across the entire income distribution rather than focusing on aggregates and averages. To do this, we use these high-level regressions and standard inequality indicators such as the 90-10 ratio, income ratio, and the Gini coefficient using global panel data. Empirically, we combine three key data sources. First, reanalysis climate data from ERA 5, which provide consistent measures of extreme weather events across countries and over time. Second, we use harmonized inequality metrics from the World Bank's Poverty Inequality Platform, and this allows us to compare income distribution across countries in a consistent way. And finally, we use standard indicators, standard metrics of economic performance, which I will go into more detail in a few minutes. So in this way, we estimate whether climate risks are regressive, meaning that they disproportionately affect lower income groups, and it allows us also to examine how these effects vary across sectors, regions, and also policy characteristics, institutional characteristics. In terms of climate risks, we consider several types of extreme weather events, including heat waves, cold waves, icing days, hot days, droughts, and extreme precipitation. I will talk about definitions in one of the next slides. So in total, the data set that we are using is drawing from 2,400 household surveys across more than 160 countries up to 2024. So I think it's from 1998 to 2024. Let me start with a brief discussion now of our data, a more specific discussion starting with the climate hazards. As I said previously, we have 6 types so far of extreme weather events that we include in our analysis, the ones that I show on this slide. The definitions are as follows. So hot days is basically the number of days above 35 degrees. Heat waves are measured with an excess heat factor. Cold waves are defined using an excess cold factor. Icing days is the number of days where maximum temperatures fall below 0. Extreme precipitation days is the 95th percentile rain exceedance days over agricultural land. And finally, drought is the number of days with affected land area. These are the climate hazard indicators that Katie and Nicole have worked on and are providing us from Tyndall. And the list is expanding, but this is where we are so far. For each of these events, we compute 2 dimensions, intensity and frequency. So intensity reflects how extreme a given event is relative to long-run historical conditions. And frequency tells us how often these events occur. We also normalize these measures so they are comparable across scales and units. And we also wanted a single synthetic index that combines these 2 aspects of frequency and intensity together into one representative indicator for each type of climate shock. So we use for that principal component analysis. I will refer to it as PCA from here on. So PCA is a dimensionality reduction technique that extracts the dominant pattern of variability from the data without assuming any prior weights. Moving on to the economic variables, we use several. We have large vectors of economic, institutional, and climate hazard variables. So speaking about economic, we use the standard ones like sectoral GDP. We consider 3 different sectors: agriculture, industry, and services, which allows us to gauge which part of the economy are most exposed to climate shocks. We also, for some specifications, we have experimented with household consumption per capita to capture living standards that GDP can miss, especially in economies with large informal sectors, such as India and other developing countries. In terms of structural variables, structural factors, we control for unemployment as a labor market indicator, domestic credit, the private sector as a measure of access to finance and recovery capacity, the share of working age population to capture demographic pressures, and female labor force participation, among others, to highlight gender vulnerabilities. We include a polarization index as defined in the work of Esteban Rentré in 1994, which is designed to capture, if you like, how divided or internally cohesive societies are. And this is a useful proxy for latent conflict potential or group-based inequality, which can amplify social consequences of climate stressors. And we also include variables, a variable for trade openness, and as well as a quality of governance indicator, a composite indicator that is built from 6 World Bank dimensions: control of corruption, government effectiveness, political stability, rule of law, regulatory quality, and voice and accountability. So let me very briefly present. We have a lot of specifications that we're churning out. I'm only showing 3 of them here. So the first one is our baseline specification. Here the outcome variable is the ratio of incomes at the top of the distribution to those at the bottom. So top 90% over bottom 10%. That is the most affluent decile divided by the poorest decile. So that is our dependent variable. On the right-hand side, we have the vector C of climate hazards that I mentioned previously, and the vector X of all the variables, economic, institutional variables that are measured in the previous slide. We also include fixed and time effects to absorb time invariant country characteristics and global shocks that affect all countries in a given year. The second specification I will be presenting today is focusing on more aggregate metrics. It's focusing on more aggregate metrics, but it's on, if you like, the overall shape of the distribution. So here the dependent variable is Gini coefficient. So instead of focusing now on only the 19th and the 10th percent and measuring the gap between these two, how it changes, we take the Gini that is essentially a measure of the shape, if you like, of the overall distribution. So that lets us see what happens to the whole regression, how it is associated with extreme weather events. And finally, the third specification I'll be showing today is a decile level regression, where essentially we see how average income within deciles is associated with the intensity and frequency of extreme weather events, plus all the other variables we mentioned previously. So let me start with showing some, showing some results. And the first table shows the specification 1 and 2 for these extreme weather events. So heat waves, intensity, let's call it times frequency. So this includes both as a composite variable, intensity and frequency. Cold waves, icing days, hot days, extreme precipitation. The first half of the table shows the 90-10 ratio. The second half shows Gini coefficients, the second specification. I'm not going to go through every row separately, but you can see it is very clear here that the message is very consistent. So if we focus on the first half of the table, you can see that the coefficients are positive, most of them highly significant at the 1% level. And that means that the gap as a result of these extreme weather events is widening, which is indicative of an association between the intensity and frequency of these extreme weather events and the inequality that is captured from these 4 columns. A similar story can be seen when we take the overall shape, the Gini coefficients. Again, in columns 5 and 8, you can see that the coefficients are all positive. I think all of them in this time is still significant. Some of them are very small, but they're positive and still significant. And again, they show a positive association overall of the shape of the distribution with the incident of the extreme weather events that we include. The next table performs the same exercise, this time for drought. Again, a similar picture. The coefficients are significantly smaller than what they were before for the other extreme weather events. We didn't find this surprising, given that drought is a slow onset event and quite often an anticipated event. So much of the impact can be smoothed through adaptation and policy responses. And therefore the short run within country income inequality can be more muted, if you like, than for sudden extremes like heat waves and floods, extreme rainfall. Moving on to the full distribution. So here is all deciles together. I've taken the agricultural sector in this slide.
Nicholas, for the sake of time, if you can conclude, let's say in 1
Yes.
or 2 minutes, so that's
Sure.
Thank you.
Yeah, so very quickly, every column here is a decile. So the bottom, column 1 is the bottom decile, column 10 is the most affluent decile. Very quickly, if you run your eyes from right to left, you will see that in this specification, all extreme weather events have reduced, if you like, real incomes. But if you are closer to the first column, you are affected more than if you're closer to the top column. So that shows that for poorer deciles, you're more likely to experience a larger fall in real incomes than in affluent deciles. So again, very consistent with what we had in the last 2 specifications. And again, very quickly, as I'm running out of time, the next 2 tables conduct some sensitivity analysis, some robustness check. So here we distinguish between agriculturally dependent economies and non-agriculturally dependent economies. In the next slide, we distinguish between different climate zones. And what we find is that you cannot have a silver bullet in terms of adaptation policy that fits everybody, because depending on whether you are, for instance, agriculturally dependent or not, or depending on what climate zone you are in, different extreme weather events will be more or less significant for you than for others. And that tells us that adaptation policy has to be context specific. We can't just say that doing this works well for everybody, but we have to look into the specific details of institutional characteristics, location, sectoral dependency, and others. So to conclude, what do we find? We find extreme weather events systematically widen income gaps. We see this in all the specifications we've tried so far. It's a very consistent result. We also say that the context, if you like, of individual countries matters. So the magnitude of inequality effects varies across climate zone, and it also varies depending on what sectors they draw most of their income from, the size of, if you like, the sectoral composition. So yeah, these are the results that we find so far. And again, yeah, thank you very much, Francesco, for allowing me to present these results. I should say these are not final results; it's work in progress. But I'm really astonished how consistent these results are across all specifications we've tried so far.
Thank you, Nicholas, for attending this webinar and presenting. And for the sake of time, I will give the floor immediately to our last speakers, Rosanne and Ann-Kathrin, and with your presentation on these pathways to resilience concept. So the floor is yours, and thank you for joining.
Thank you, Francesco. I hope everyone can hear me.
Yes, we can hear you and see you.
Great. So thank you again for attending, and I'll be presenting on the EU project SPARCCLE, which looks at socioeconomic pathways, adaptation, and resilience to a changing climate in Europe. And I'm here with my colleague Ann-Kathrin Petersen, and we are part of the work package that focuses on climate risk and adaptation pathways. But we will do a little bit of a larger description of the project in a couple slides so that folks understand where we sit in the broader project. So next slide, please, Annie. Thank you. So the goal of SPARCCLE is to support risk-based decision-making in Europe. And to do that, we have multiple levels and levers that we use, and that includes delivering on new climate impact frameworks that utilize emulators for hazard development, different impacts that we model, and different ways of looking at vulnerability. And so we have a probabilistic approach that we apply for assessing climate impacts and extremes in Europe. And we do that, and we integrate those probabilistic methods for impacts with multidimensional vulnerabilities. And so we have work packages that are dedicated to those, as well as to adaptive capacity metrics. And we combine those to assess risk and to assess the potential for risk reduction through adaptation and through adaptive capacity. The project has a strong stakeholder engagement and co-development process in that it develops stakeholder co-developed scenarios, including stress testing scenarios that go beyond the SSPs, but also include the SSPs, to understand the different kinds of environments in which we need to assess risk, and that stakeholders are interested in understanding risk. Next slide, please. We have a number of project partners, over about 13 or 14 project partners, and we work in this pillar concept where we have, as I've said before, climate hazards and impact modeling, multidimensional population and vulnerability modeling projections into the future. We look at direct and indirect damages and assess those using a risk model called Climata, and we also use that risk model and look at adaptation options within that risk model at the sectoral level. And then we have a pillar that's looked at integrated assessment modeling for mitigation and for socioeconomic implications. And as I've said, we have a strong stakeholder scenario co-development that moves us from fast track scenarios, which is the stage 1 of testing out our large inter-modeling comparison and data passage from one team to another, to getting at the kind of scenarios that stakeholders are interested in. Next slide, please. So as the focus of this talk is on risk and adaptation, I will focus here on how we do climate risk modeling in SPARCCLE. We use a platform called Climata, which is a catastrophic risk modeling framework, and we combine hazard, exposure, and vulnerability to compute risk. In our case, we are interested right now in the fast track scenarios. We have looked at extreme heat and extreme precipitation as the hazards, and are looking for exposure at the European population at the NUTS2 level, where we combine nightlight and population census to get at exposure. And then in terms of vulnerability, we have two components. We either look at the percentage of people that are exposed to a particular hazard, or we look at hazard-specific fatalities, and that influences the vulnerability curve. So in the first set of results, I will be showing results from the fast-track scenarios for extreme heat, and I will be focusing on the percentage of people that are exposed to a particular hazard. And later on, we will get into, in the outlook, what that can mean in the future, looking at different scenarios and different means of vulnerability. So next slide, please. So the first set of results that we have focus on average annual percentage of the regional population that is exposed to extreme heat. We're similar to other colleagues in other projects. We're looking at daily temperatures that are above 35 degrees. We use downscaled mesmer emulations combined with demographic changes, median trajectories of global mean temperature, and a step function for vulnerability, where we're saying at first, if the temperature is below 35 degrees, no one is exposed, and if it is above, then everyone in that population, in that area, is exposed and impacted by this hazard. And so if we first have the first set of results of the map, is the map on the left, where we have the percentage of exposed population, where warmer colors means that more of that population, a higher percentage of that population in the country is exposed. And you can see that the lower half or lower parts of Spain, so most of the Iberian Peninsula, parts of southeastern Europe, and the lower parts of Italy are the ones with the highest annual average annual percent of their population is exposed to extreme heat The map on the right then takes the average of these mean impacts, so the average of these downscaled Mesmer emulations, and then projects in the future, so between 2070 and 2100, and then shows the difference, so the change in the exposed population. So warmer colors, and as all of the colors are warm, means that more people will be exposed. And we see that the greatest changes are occurring in western and southwestern France, Italy, and parts of southeastern Europe. Next slide, please. We can also, in these emulations, not only focus on the mean, but we can take the worst case realization out of these to again see where the largest changes will be. So now we see in the worst case realizations, we are still in southern France, or we're in most of France actually. We see some large changes as well in northern Spain. We see large changes as well in Eastern Europe. So these become the sort of regional hotspots that we can see using at least a fast track analysis for extreme heat in Europe by the end of the century. And so if we go to the next slide, we heard from the colleague in ACCREU that funding, or that financial motivation, or the financial effectiveness, sorry for the poor language on my part, will not be as big as the socioeconomic drivers, right? So a lot of the impetus will be on governments, on public financing, the public purse, to be able to finance adaptation. In Sparkle, we're using a model called CATSIM, which estimates the total available financing resources from governments to address climate risk. And so now we're able to see the available public finance resources from budget diversions, or from credit buffers, or from contingency credit, or domestic credit that can offset or pay for these climate impacts that we see. What CATSIM can do is then compare the hazard-induced government expenditure needs to its available financing resources, and thus report something called the fiscal gap year. And that is the probability of running out of financing resources due to a particular hazard. The image shown here is from a separate report outside of Sparkle to show you roughly what these kind of results can look like. So warmer colors means higher risk of running out of these financing resources, and cooler colors mean a lower risk. And so now if we go to the next slide, we can see what the initial results from our fast track scenarios are. First, we see that the total available financing resources to Europe is 260 billion, and this is the sum of every EU country. And that we end up, when we do this analysis, with an average fiscal gap year of 27 years. That means that every 27 years, Europe will have this kind of gap where it'll run out of finances to the hazards. What we see is there's an annual average fiscal gap of 10.35 billion euro. So the expected shortfall of public finances each year at the European scale is 10.35 billion. So these are the two sets of results on the risk side. And now my colleague Annie is going to talk about the concept of adaptation pathways, how they help us to sequence adaptation measures to the risks that we've seen before.
Yeah, thanks a lot, Rose.
Yeah.
I hope you can all hear me now.
Yes,
So-
yes, we can hear you.
Perfect.
Absolutely.
Thanks.
And just, I mean, if you can compress a little bit the presentation, because we are running out of time. So
Okay,
let's
I'll
say
do my
5-10
best.
minutes.
Yes, I'll do my best. So yeah, as you already saw from the fast track results that Rose has just presented, there is a range of possible futures. So this means that the aim should be to inform adaptation policy and decisions that are successful across a variety of futures. So the key is really to identify robust and flexible adaptation options. And that is why we turn to the adaptation pathways approach. Another slide. Exactly, which is an approach to support robust and adaptive long-term planning and decision-making. which explicitly considers uncertainty and includes flexibility into the planning. And adaptation pathways can be defined as sequences of actions which can be implemented progressively depending on how the future unfolds and depending on the development of knowledge. And the dynamic adaptive policy pathways is one widely used approach to develop such. And then once you've done an adaptation pathway development, you kind of have a resulting adaptation pathway map, like one here that is illustrated here. And this is developed kind of by assessing under what conditions we need to adjust or add adaptation measures to our adaptation strategy. So it really depends on the different thresholds of the adaptations and then helps you to map out the complete solution space in order to keep the risks and the impacts to an acceptable level. And now in SPARCCLE, we kind of want to move this from case-specific adaptation pathways to try to develop more generic adaptation pathways and explore their possibility and utility in order to also inform adaptation scenarios for impact modeling and also to still then, inform local decision makings to allow also more nuance of adaptation, both in the SSPs and scenarios, but also, to provide more guidance on multiple levels. And for that, we are looking at different key sectors and risks. And the first one that we have focused on most for now is the heat extremes and human health. But there's also further sectors that we look at, including flooding and settlements, forestry and wildfires, and drought and energy infrastructure. And so for those, we are developing those adaptation pathways right now and have already clustered and identified a large range of possible adaptation options and are developing, the pathways. So this is to be presented in the next webinar next year then. And then further, as was also mentioned before, we also try to take this further step then to link the adaptation pathways to the stress testing scenarios that we are developing within our project to really identify the robust strategies and then also to link the adaptation pathways to the SSPs to allow for, this generic level, which then also allows for more nuance in the representation in impact models. And one issue that was also mentioned, I think, in some of the other presentations is the quantification of the effectiveness and also the future effectiveness of options, which is also one of the challenges that we are working on and where we also are very grateful to interact with our sister projects. And with that, and I think in light of time, I'll pass back to Rose for some concluding remarks.
Yeah, thanks, Annie. Right, so the next steps will be to pull in the work that we're doing on hazard-specific vulnerability curves into the risk modeling that we're doing. There have been some initial results and those are being iterated upon, and we will be rolling those out first for heat and then for the other hazards that Annie has pointed out just a moment ago. We'll be looking at the responses from the government side, so in terms of fiscal gaps and risks, and finalizing the adaptation pathways and scenarios for the integration, both in Climata and into the IAMs. We've done work on the fast track scenarios, and we will now head over to the stress testing scenarios, where we would look at these exceptional yet plausible changes in climate and socioeconomic risk. And we will be developing EU scoreboards and dashboards so that these results can be visualized. So with that, I will stop here. Thank you everyone for your time and your attention. And I pass back to Francesco.
Thank you. Thank you, Rosanne. Thank you, Anne, for the presentation, also for staying in time. So highly, really appreciate it. So let me, unfortunately, we don't have time to now address potential questions, but we kept track of the questions that have been raised in the chat, and then we are going to address them to the presenters, and maybe maybe for sure they will be happy to answer the question. And we are also planning to make this presentation available to our audience if the presenters agrees, of course. And we likely, we shall just visit and stay tuned with our website, CMCC events, where we are going to give the indication where to find the presentation or post the presentation there directly. Okay, with that said, I would like to again thank all the presenters for the very interesting work that is being done. I would say that I've seen new either new results and also new methodologies applied. So very, very interesting. And I think that there is ample room for collaboration on these issues and topics. Let me also thank all our public or our audience for having stayed with us, and hoping that this was something of interest for you. And let me also, given that I think that this will be for sure our last webinar for the year, to wish you a Merry Christmas and hopefully happier New Year than this year. Okay, so with that said, thank you all again, and see you next time. Anyway, stay tuned with our website, where we're constantly updating on the events and the activities and webinars and seminars that we are giving, and also visit the website of our colleagues institution, because they also have a lot of interesting work and activity going on there. Okay, thank you very much, and see you next time. Bye bye everyone.
Thank you. Bye bye.
Bye.